3, 2, 1, go.
This is the presentation for AISI 34 stainless steel. We are a gamma group, and this is for the MSE 2101 Spring 2023 Section 1.
Hello everybody, my name is Taha Ali and I'm a chemical engineering senior.
I'm Maddie Archambault.
I'm Owen Bad.
I'm Gabriella Bosch.
I'm Wendy Tartani.
So 34 stainless steel is also known as UNSS 30400. This chart shows how this alloy is referred to in different parts of the world. 34 stainless steel is made up of 8 different elements as seen in this table, but is primarily iron, chromium, and nickel. This type of stainless steel is very common in everyday life, from the pots and pans that we cook with to appliances to heat exchangers. 34 stainless steel is primarily face-centered cubic. The 300 series stainless steel alloys are referred to as austenitic because they consist predominantly of the austenite phase in the annealed condition. They are also the most common type of stainless steel. The face-centered cubic structure exists at all temperatures. Austenitic stainless steels have moderate to high nickel content ranging from 8 to 12%. Their high manganese and nitrogen content stabilize the austenitic structure. However, the addition of these elements make them more expensive. All steels are an alloy of iron and other carefully selected alloying elements. Pure iron exists normally in one of 2 main kinds of crystal structure. Alpha iron with a body-centered cubic lattice, forming material known as ferrite, and a gamma iron face-centered cubic lattice, forming austenite. When carbon is present, then a further crystal structure can be formed that results in another material, martensite, which is a body-centered tetrahedral structure. 34 stainless steel is austenite made from gamma iron, so it concluded that it is likely to have a face-centered cubic unit cell. 34 stainless steel can also be converted to body-centered cubic by a magnetron sputtering method, which was found in the study Magnetic Properties of Metastable 34 stainless steel with BCC structure. The researchers were able to convert 34 stainless steel with BCC and back to FCC by changing the temperature. The equilibrium phase of 34 stainless steel would have an SCC structure at this 300 series stainless steel is typically austenite, which attributes to its equilibrium phase structure, and a non-equilibrium phase of 34 stainless steel has a BCC structure.
34 stainless steel has many processing methods, and these are the 8 following processing methods. First one is the melting the raw material, removal of excess carbon, tuning or stirring, forming the metal, work hardening, heat treatment and or annealing, cutting and shaping, and as well as applying surface finishes. From the processing method, heat treatment, the stainless steel is actually decreased in terms of strength, and by the processing method of cold working, it is actually increased in terms of strength. So how does processing method exactly affect 34 stainless steel? As we can see on the diagram, after hot rolled, through a reduction being cold rolled, we can see a deformed austenite, which actually reduces the increase of strength because it is more cold rolled than its limits. And then after annealing, we can see that the austenite is more refined and it's a little bit more stronger. So how does cold working and work on 34 stainless steel? Cold working increases strength of 34 stainless steel by introducing dislocations to the material. These affects crystal lattice structures that occur when the atoms are displaced from their ideal positions. When the material is actually subjected to external force, such as cold working, the dislocations move and interact with each other. This process is called work hardening, and it leads to an increase in strength. But however, an excess of cold work can actually reduce the decrease in ductility and toughness for 304 stainless steel. As the amount of cold work increases, the dislocations become more tangled and the material becomes more brittle. This reduces the material's ductility and toughness, making it more prone to fracture and failure under stress.
And also analyze 304 stainless steel using phase diagrams. Here we have a phase diagram of nickel and iron, and we can see that 304 stainless steel, or also called austenitic stainless steel, is found in the gamma iron part of the graph, and there nickel is at 30% composition. We can also take a look at ternary phase diagrams, which give us a little more information about the elements present. And we can say that austenite stabilizing elements are manganese, carbon, and nitrogen. Another important fact about 304 stainless steel is its nucleation site. And basically it takes some incubation time for the nuclei to form, but it does proceed at a more rapid rate as more nuclei develop and grow. At higher temperatures, the diffusion rate of carbon increases and austenite forms more rapidly. We can also take a look at these two pictures over here, which basically show how much nickel is in austenite. At 8% nickel, it's called austenite or 304 stainless steel. Another diagram of grain size is on the right, and grain size is really important for many characteristics of steel, such as hardenability and microstructure transformation, which depends on grain size.
To sum up some of the mechanical properties, we've displayed a chart of properties for different conditions of stainless steel. To sum them up, the tensile strength of stainless steel 304 is most commonly 585 megapascals. The yield strength is often around 235 megapascals, and also the Brinell hardness is about 149. Next, we have how a specific processing method can impact certain mechanical properties. On the left, there are images of how different amounts of cold rolling affect the microstructures of stainless steel. As you can see, the grains are flattened and get smaller as more cold rolling is done. On the right, we have a graph that compares the percent deformation to the hardness of the steel. Due to the changes in the grain size caused by cold rolling, the hardness of the material will increase significantly. The cold rolling process can cause austenite to change to martenite, though, which makes the material hard but brittle. This is why stainless steel 304 can be annealed after cold rolling. The heat treatment will restore the ductility of stainless steel 304, and it is commonly known for that. Next, we just have an engineering stress per strain curve under several different conditions that highlight the ductility of the steel. And we have a second engineering stress per strain curve that does the same thing. If you look at it, you can see that lower temperatures, there's a high ultimate tensile strength due to the strain hardening, but there is also a lower ductility, which leads to a more brittle steel. The ductility is a maximum between 0 degrees and 25 degrees Celsius, and at warmer temperatures, there is a decrease in ductility and strength as well.
Type 3/4 stainless steel is not magnetic, but it may be slightly magnetic after cold working when it is heated. When it is heated, it becomes sensitized and its corrosion resistance is lowered. This chart shows other properties such as density and thermal conductivity. Improving corrosion resistance and electroconductivity with coatings is also important for some of 3/4 stainless steel's uses. Adding carbon film will improve the corrosion resistance and electroconductivity. The graph on the left displays that since the carbon coating 3/4 stainless steel has a more positive potential than plain 3/4 stainless steel, that means that the coated 3/4 stainless steel has a higher corrosion resistance. Corrosion resistance is one of the main attractions of using 3/4 stainless steel, so being able to improve this with coating is valuable to the industry. The graph on the right displays that since the carbon-coated 3/4 stainless steel has a lower interfacial contact resistance than plain 3/4 stainless steel, it means that the coated 3/4 stainless steel has a higher electrical conductivity.
So some other properties. The strength of ASI 304 stainless steel is affected by several factors, including the amount of cold work and annealing temperatures, as previously explained. Additionally, the annealing temperature and time can be tailored to achieve the desired properties of ASI 304 stainless steel. For example, annealing at higher temperatures for longer periods of time can result in larger grains, which can improve the material's resistance to intergranular corrosion. On the other hand, annealing at lower temperatures for shorter times can result in finer grains, which can improve the material's strength and ductility. In addition to strength, the microstructure of the stainless steel also affects other properties such as corrosion resistance and formability. The high chromium and nickel content in the alloy promotes the formability of an oxide layer, of a passive oxide layer on the surface, which enhances its corrosion resistance. So some applications. 3/4 stainless steel is widely used all over the world because of its exceptional corrosion resistance and affordability. As seen by the list of all these applications, it's considered one of the most used stainless steels on the earth. The reason for its popularity comes from the material's characteristics. Some of these characteristics are the corrosion resistance specifically towards oxidizing acids, which makes it easy to sanitize and leads to it being good in kitchens and food applications. It also has very good drawability, which allows for it to be fabricated into very complex shapes due to its high elongation and yield strength. Additionally, the austenitic structure of the steel results in excellent toughness, making it ideal for the normal wear and tear on these appliances.
And these are our references.
Thank you.